Now the next unit that we're going to be looking at is work and energy. And today we're just going to look specifically at work. And so work, as defined in your formula sheet, is just a force times a distance. And so whenever you have a force acting on an object and causing a displacement, you are getting a transfer of energy from the object from the one that's producing the force to the one that's then experiencing that force. And so that energy transfer is what we refer to as work. Now on your formula sheet, it just has work equals force times displacement. And what you need to watch with that there is that force can be different things depending on what's being asked for. So make sure that you're reading really carefully as you're going through. The terminology is going to tell you which force you need to use in that net equation there, or in that work equation. So just watch carefully for that. So there's kind of four main cases that we're going to have. Probably the most common is when you're looking at the work done on the object. And that's always going to be then this applied force. And so if you see that phrase in the question, what's the work being done on the object? Then you're just going to take the force applied, multiply that by the displacement, and that's going to be the work done then on that object. We can also talk about the net work being done. And if we're talking about net work being done, and this one's fairly intuitive, then we're just going to use the net force in that equation. If you're looking for the work done by friction, that's going to be then, of course, the friction force. And if you're looking at the work done against gravity, that's going to be the gravitational force. And whenever you're working going up, then you're working against gravity. And then if you're lowering it down, it's work done by gravity. But in either case, then you can use that F of G. Now, in terms of the graph, if you have a force versus displacement graph, the area under the graph is going to be equal to the work done. And that might be, say, a rectangle, triangle, or some combination of those. The reason for that, if you look at your equation, we have work equals force times distance. If the two quantities, the x-axis variable and the y-axis variable, are being multiplied in your equation, whatever they're multiplying to come to, that's going to be represented by the area. If you had a work divided by a displacement graph, then the slope would be equal to the force. Or if you did work divided by force, the slope would be equal to the displacement, because in that case you have the y-axis variable divided by the x-axis variable. But more commonly, you'll do a force distance graph, and then you're going to be looking for the area to get then the work being done. Now, work and energy are both scalar quantities. And what that means is that when we are reporting work, we don't include a direction with that. However, it is still possible that work can be positive or negative. And this is just really looking at what is your reference point, so which object are you looking at, and then what are the relative directions of the force and displacement. So if the vectors are in the same direction, positive work is being done. And so if you think of yourself, say, pushing up a box up of a ramp, if you're moving the box up the ramp and you're applying that force, of course, to make that happen, this is positive work. So the person is doing positive work on the box. It is also true, though, that we could look at it in terms of the box. And so if you're pushing this way on the box, remember, because of Newton's third law, the box is pushing back with an equal and opposite force. Now, the force that the box is exerting back on the person is opposite the direction of motion. So we could also say that the box is doing negative work on the person. Now, typically we phrase this in terms of what the person is doing, but it would be valid to do it in terms of the box's perspective as well. And so we can really always look at both positive and negative work, depending on which object we're focusing on. So if you are, say, pushing on a box and the box is really too heavy, it actually just ends up pushing you back down the ramp, you're applying the force in the upwards direction. Should be an arrow here. If this displacement is pushing back down on you, so the box is actually pushing you down, you're doing negative work on the box. But now that equal and opposite force from the box is in the same direction as the motion. And so in this case, if the box is actually pushing the person down, the box would be doing positive work then on the person. And so you can always really look at positive and negative work. But remember, the overall work value is a scalar, and so we don't include directions for those. So it's measured in joules, the same as we have for energy. If you just look at our equation here, we have work equals force times distance. And remember, to come up with the fundamental units, we can just put in our values. So work is measured in joules, force is measured in newtons, and your distance is measured in meters. Now, the newtons is still not a fundamental unit, but a newton, remember, is a kilogram times meters over seconds squared, and then still times meters. And so then we get meters times meters, and that gives us then kilograms times meters squared over seconds squared. And that's then the fundamental units then for the joule. So for this question, we have a 40 kilogram object being accelerated from rest to a speed of 5 meters per second over a time of 8 seconds. And so these are kinematics quantities, of course, whenever you're dealing with velocities and times. And remember that with these ones here, we are going to be bringing kinematics in. So your work is equal to force times displacement. This displacement may be given, or you might have to calculate it using a kinematics problem or equation. Remember that force it can also be related, if it's the net force at least, to a mass times an acceleration. And so very often we'll need to get the acceleration into here whenever we're dealing with, say, a net force, or sometimes even with the total work being done on the object. So kinematics will come in for these, to play in these, and primarily looking for displacements and accelerations. We're also given the coefficient of friction here, and so we can put that into our force equation. But just to start with, I'm going to come up with the displacement and the acceleration using then the kinematics, and then we can start to look at the forces and the work done. But very often you'll need the acceleration and displacement from kinematics. So I have a VI that's equal to 0, I have a VF that's equal to 5, and then I have a time that's equal to 8. And what we'll be looking for then is both acceleration and displacement. So given these variables here, I can find the acceleration with the VF minus VI equation. So VF minus VI over t. And so then I'll get 5 minus 0 over 8, so just 5 over 8. And that'll give me then an acceleration of 0.625, and then of course meters per second squared. Again, using the same set, we can find then the displacement. Now at this point we could use a number of different equations to find the displacement because we also know the acceleration, but I will try always to find one using just the original variables given, just so that if I make a mistake here, it doesn't get carried over into the displacement equation. So here I'll use the sum of the velocities over 2 times time, so VI plus VF over 2, and then times your time. And so your displacement then, just 0 plus 5 over 2, and then times 8. And so that'll give me a displacement of 20 meters. The next thing I'll look at is my free body diagram. I'm going to do that just because I'm looking for different types of work. So my friction force, the net work, and then the work done on the object. And so I just want to get an idea of what forces I have there. And I'll have to do some net force equations then to get some of these as well. So first of all, we have a box that's being accelerated from rest by some force applied, which means I have a force applied heading in this direction. And that's the one I'm going to be interested in when I'm looking at the work done on the object. We're told we have friction, and so I'm going to have a friction force then heading backwards. And that's, of course, the one I'm going to need when I'm looking at for work done by friction. And then we also have then the force net. Now we're told it's accelerating forward there, so that has to be in the same direction as the force applied. And that's the force I'm going to be interested in for the work, the net work being done. And so I would recommend finding acceleration displacement using kinematics. And then also when you start working on these ones here, do draw the free body diagram for those, especially for that force applied and the force net. That can be something you want to watch out for. Now for part A, we're looking at the work done by friction. Now the force, or work done by friction, is going to be the force of friction times my displacement. So if we find our force of friction, then we can just take that, multiply it by 20, and that'll give us then the work done by friction. So your force of friction, remember, is that value mu times your force normal. Now your force normal on a flat surface is just equal to mg, and so we'll have mu times the mass times g. And so we have our mu value of 0.02. Our mass is 40 kilograms, and then times g. So that's going to give us a force of friction, 7.848. That'll of course be in newtons. And then we can just put that into our work equation of 7.848. It's in newtons. We'll multiply that by the 20 meters, and that'll give us then a work of 157 joules. Now one thing to watch as well here is the force of friction is in this direction. My direction of motion is in the forward direction, so I will put a negative in here as well, just because this force of friction and the displacement vector are in opposite directions. And you could then just put that in with one of those as well, or you can just think about that at the end. But if your force of friction and your force and your displacement are opposite in direction, you need to have a negative then for the work. So watch carefully for that. For the second one, we're looking at the net work being done. And so for this one here, if I look at the work net is the force net times the displacement. The displacement will be the same for all of those. It's just the forces that are changing. Now my force net, remember, is just mass times acceleration. And so I calculated the acceleration with my kinematics. And so for my force net will just be 40 kilograms times that 0.625, which will be then the acceleration of the object. And so I get a net force of 25.0 newtons. I can put that into my net work, And so I'll get then 25 newtons times the 20 meters. And so I get a net work of 500 joules. Now for the last one, I am going to need to do my net force equation. And watch this carefully whenever you're dealing with the force applied. So for part C, we're looking for what's the work done on the object. And that's going to be this force applied here. And so I need to do my net force equation in order to get that force applied. And once I have that, then I can just use force applied times distance. So for C, work done equals force applied times displacement. That's the work done on the object. And don't forget, you have to do net force equations for those force applieds. So my force net is in the same direction as my force applied, but opposite in direction of my force of friction. So when I isolate force applied, I'm going to end up with force net plus force of friction. Now I have both of those values already, so you could put in the mu mg and the ma, but we also have for our force of friction up here, we've calculated our force of friction as 7.848, and then our force normal as 25. So we can just put those values in and get that done a little bit quicker. And so that'll give me then a force applied equal to 32.848, and that'll be of course in newtons. So we can put that in for the work done on the object. We get 32.848. We'll use the whole number, of course, from our calculator. Multiply that by 20, and then we end up with 657 joules for our final value. Now you will note that it's going to kind of mirror the force net equation, or the net force equation here as well. So my force applied is the force net plus the force of friction, and so this is also going to be the work done is going to be the work net plus the work done by friction. And so we see that 157 plus 500 is going to give us a 657, and that's just because the distance is the same for both. And so if our force applied is dealing with the sum of the forces times distance should end up with the sum then of those work values there. So just be really careful with that. Again, watch carefully your terminology. Work done by friction. This is the only one that's opposite the direction of motion, so that's the one that's going to be negative. Force net, force applied are both in the direction of motion, so those are both going to be positive. And just make sure then that you're using the correct force net, force applied, and force of friction to calculate those. So a simple machine, these are things like levers, ramps, and pulleys. You can use those then to either increase or decrease the force required to do something. And the factor by which that's going to be increased or decreased then is the mechanical advantage. And so if you can decrease the force required by a factor of 4, then you'll have a mechanical advantage of 4 times. Now the flip side of this though is that you always have a trade-off with displacement. And so the more you increase the force, the less distance you require, or the more you decrease the force, the more distance you're going to require. And so those two are always going to be going in different directions. Whatever change you have in the force, you'll have an opposite and proportional change in the displacement. And what that means then is that simple machine is not going to reduce the amount of work that you're doing. Your simple machine is going to have the same amount of work as if you had done the same task without, because you're just trading off force and distance. And because the work is the force times the distance, any decrease in one, if accompanied by an increase in the other, is going to work out to be the same. Now that is also for the frictionless case. In actual fact, because there's friction, the simple machine tends to actually increase the work a little bit because that longer distance means you're going to have a greater contribution from frictionless or from friction forces. But for our purposes, we're just going to be dealing with a frictionless surface, and so we can assume that with and without the simple machine, the amount of work done is going to be exactly the same. And so just looking at an example of that here, we have a 20 kilogram mass, and we're going to look at moving that to the top of a ledge with or without a ramp. And so we're lifting a 20 kilogram mass to the top of this 3 meter ledge. And we're going to look at 2 ways of doing that. One is if we lift it straight up, and the other then is if we push it up a 9 meter ramp. And so what we see first of all is that the distance required for the ramp is going to be 3 times the distance required for the mass. And so what we're going to be expecting is that this increase in distance of 3 times should reduce the force then also by a factor of 3. And we should be able to calculate and show that that's going to be true. Now I'm going to keep a constant speed for each of these just for simplicity. So the force net, in this case here, is going to be a force applied minus the force of gravity. And so we're going to have to exert a force straight up. That'll be the force applied. But that's counteracted then by this force of gravity. And because we're at a constant speed, our force net is 0. So the force applied that we need here will just be equal to that force of gravity. And so my force applied will just be mg. I'm lifting a 20 kilogram mass. And so the force applied will just be 20 times g. or 196.2 newtons. Okay, that'll be the force applied. My distance, though, is only going to be 3 meters, and so then when I look at the work done, I can then just take that 196.2, multiply it by 3, and I'm going to get a work done then of 589 joules. And so that's going to be then the work done, lifting it straight up then from the ground. So then we can look at what happens when I do the same thing on a ramp. And so my free body diagram changes here a little bit. So I do still have this force applied that's being pulled up the ramp, but now it's not just the force of gravity that's counteracting it, it's that force of gravity and force normal, which then we combine to be the force parallel. Now I'm still at a constant speed, and so I can still take a net force of 0, but I'll have my net force equals then force applied, now minus that force parallel. Force net is 0, and so my force applied will be equal then to that force parallel. Now my force parallel, remember, is mg sine theta equals my force applied. Now for this one here, sine theta, and I have this angle. Now we could just calculate what that angle is. We can also just use the ratio, because I know that sine theta is equal to the opposite side over the hypotenuse. So this is going to be equal to 3 over 9. So I can replace this whole sine theta term with actually just 3 over 9. And so then I'll get 40 times g times this 3 over 9. And that's just because sine theta is the term here, and sine theta is equivalent to 3 over 9. You could just solve for the angle too and put it back in, but this will be a bit quicker. We can also see then that 1/3 reduction that we're looking for here. So since the ramp is 3 times as long, I'm basically getting a 1/3 reduction in what the gravitational force was over here, this mg. And so if we put that one in, we're getting 65.4 newtons then as our force applied. The flip side, though, remember, is now we're going 3 times as long. So we have a reduced force, and so certainly that's helpful because 196 would be a lot of force to put up or push up. If you can then reduce that by 1/3, that's a lot easier to push that object up the ramp. Again, the trade-off is that you have a longer distance over which to apply that force. And so you can take then the work that we have the force, again, times the distance. And this will be force applied because we're looking at the work done on the object in each case. And so that's why we're using force applied here. And so I can take that 65.4. Now I'm multiplying it by a value of 3 times, so 9. So I have 1/3 the force times 3 times the distance. And so then I'm still going to get that 589 as the overall work being done. And so in the frictionless case, you don't save any work using a simple machine, but you can make that work easier to do because you can reduce the force then over which that's going to be applied.